Well, I appreciate the invitation to be here, first of all. So thank you, Professor Benedict. And you can all call me Dane. That's fine for having questions. This is great. I mean, I think it's very exciting. You're putting together this kind of hackathon, and glad to be able to make my little contribution here. So I'm going to talk today about some of the work we've been doing looking at fast oxygen materials. So these are just materials that move around oxygen a lot. I want to start by acknowledging our sort of team of students and collaborators who really did all the work I'm going to be showing. Ryan Jacobs and June Liu and Sariful Sheikh are postdocs and staff in my group. Jay Liu is at the National Energy Technology Laboratory and has been an essential contributor to this work. And then Maciej Polak is also a staff in our group, and he's been doing the natural language processing stuff I'll talk about towards the end. And I want to acknowledge our research group and everything they do to just keep everything functioning. And of course, funding from a number of different sources over the years for different aspects of this work, both financial and computing, which is essential. So let me jump in. It's kind of three parts to the talk. One is I just want to say a little bit about fast oxygen materials and why you would care about them. And then go through an effort we did sort of trying to discover new ones and show a little bit how that works. And then talk about some of how we're trying to shift to more data-centric approaches to the same problem. And that's really work in progress, but I think illustrates some of the interesting techniques that are out there and some of the pros and cons versus more traditional type approaches. So let me just say a little bit about fast oxygen conducting material. So what is a fast oxygen material? It's just a material that moves oxygen quickly through it or across its interfaces, like out into the air. And there's a lot of technologies that make use of this. Solid oxide fuel cells are kind of the core focus for the work I'm showing here. But there's also solid oxide electrolytic cells that split water. Oxygen sensors need these kinds of materials. Gas separation membranes use these kinds of materials. Chemical looping, which is a technique for driving certain kinds of chemical reactions. Memristors are a newer technology that makes use of a lot of fast oxygen materials. So it's just a very valuable class of materials where you can use them to bring oxygen to where you need to in the ways that you need to. I'm going to focus on solid oxide fuel cells, so let me show you how they work in this context. This is a schematic of a solid oxide fuel cell. On the left, you have, let's see if I can get my pointer working. Okay, hopefully people can see a pointer there. On the left, you have oxygen gas coming in. It hits a fast oxygen material and gets split into oxygen ions, which then move through an electrolyte, which is another fast oxygen material. And then they go over to the anode where they find a hydrocarbon of some kind, react with the hydrocarbon, form carbon dioxide and water. And that overall process, because it goes through an electrolyte where electrons can't flow, the electrons get dragged through an external circuit. So that chemical reaction can be used to move electrons through an external circuit. And that's essentially how a fuel cell in general works, and in particular, a solid oxide fuel cell. So you can imagine that moving oxygen through these cathode and electrolyte is really critical to the performance of these types of devices. So why do we care about fuel cells, and particularly solid oxide fuel cells? The traditional arguments have been essentially that they're a better internal combustion engine. So instead of burning fuel in traditional lighting it on fire and making heat kind of way, you're burning it electrochemically. And they can be significantly more efficient than burning it with traditional combustion. And there are many efforts to try to build like distributed power sources where you could use natural gas. You can make a high energy density, very efficient engine that you might put on undersea vehicles or unmanned aerial vehicles. People are exploring them for auxiliary power, for trucks, things like that. Bloom Energy is a famous company in the US that does this. They create servers that you can essentially use for taking your building off the grid and running it off of natural gas in a very efficient way. This is great, but is still a CO2 producing technology, and there's a lot of interest in utilizing these types of energy technologies for moving us away from CO2 production to help with global warming problems. And that's created a lot of new opportunities in this space because these are a very efficient way to burn hydrogen. So if you are thinking of a more hydrogen-centric economy, where you generate hydrogen, ideally through an entirely CO2 neutral source like solar energy for splitting water, then these become a very efficient way to burn that hydrogen. And people are very interested in using them in that context. And they have a particularly interesting quality, which is that even in the hydrogen production, you can essentially run a solid oxide fuel cell in reverse, put energy into it, and split water to make hydrogen. So there are interesting opportunities where you integrate its ability to create hydrogen and then use that same hydrogen as an energy storage and productive system that can be created in a way that doesn't make CO2. So those are some of the areas that people are exploring for utilizing these solid oxide fuel cells. So we're interested in trying to improve these technologies. So let me first explain one of the challenges of using them. And it has to do with what's called the area-specific resistance. That is basically the resistance in the cell, which is basically the inefficiency. So you should think of this axis as how inefficient the fuel cell is. So it's bad to be high on this axis. And what happens is as you cool down a fuel cell, the resistance or the inefficiency due to each of its components tend to go up. And in particular, you get an exponential increase in losses at one of the key components, which is the cathode of the fuel cell. And this is due to the fact that it has to drive a pretty complicated chemical reaction of splitting oxygen. And as you go to lower temperatures, that gets very inefficient. And we would like to go to lower temperatures because if you look at this temperature scale, right, typically people operate at modest inefficiencies, which is up near 800 Celsius or so. 800 Celsius is really high, right? If you're thinking about a technology you might put in your cell phone or something like that, you don't want to be at 800 Celsius. Even if you're using it as a backup server somewhere, something like that, as an energy server, it's at 800 Celsius, you're going to get a lot of interdiffusion of components. You get degradation mechanisms. It's challenging. And so there's an interest in lowering those temperatures, but then you get significant increases in efficiency. So there's a lot of exploration of making materials that can execute the key operations of the fuel cell at a lower temperature without losses of efficiency. And we're going to focus on cathodes. So what does the cathode have to do? It has to take oxygen gas into it, do some magic catalytically, and spit out oxygen 2- ions into the electrolyte. And that is essentially the process that it is trying to do, and that we want to make happen more easily and faster at lower temperature. Here's a little more detail on what happens in that process. Typically, oxygen comes in as O2, lands on the surface of the material, finds a vacancy in the oxygen sublattice of the cathode. It's typically an oxide material, incorporates into that cathode, and then transports through it as an O2- ion into the electrolyte. So that fairly complex multi-step process is what we want to optimize to make a better cathode material. And what we want to do is try to do this using molecular simulation. So my research is primarily computational. So I want to use molecular understanding and increasingly data science type tools to be able to search for these types of materials, design and optimize these types of materials. And that's kind of the question in front of us. Can we do that? And I want to show you one example where we've had some success. So we're going to look in a very specific space of materials called perovskites, which you may have run into in different contexts. They're widely used across material science. They have known good performance for this type of cathode oxygen reaction. They transport oxygen quite quickly through some of them. Some perovskites can exchange oxygen quite quickly. And a number of the solid oxide fuel cells that are commercial today, this is a commercialized technology, use perovskites for their cathode. For example, lanthanum strontium manganate is the workhorse cathode for the industry. The Bloom Energy servers that I showed you outside of eBay in that picture, those have a lanthanum strontium manganate cathode in them. Lanthanum strontium cobalt iron is a little bit higher performing material, although it has some degradation challenges. But there's a whole zoo of possible materials, many of which people have already discovered that are higher performing. They always have some issue of stability, some issue of conductivity, some issue of thermal expansion. So they haven't been commercialized, but there's a vast space to look in, and it's hard to do that search just as a human. I mean, it's time consuming to make any given sample and measure its performance. And the space is very large. It's actually been estimated that you can dope 90% of the periodic table into this perovskite structure. So there are hundreds of thousands of potential perovskites we might make, or millions or hundreds of them. And the question is, which ones have the highest performance and are the best ones to spend time on for further experimental investigation? So we're going to first just look at that with really a computational screening technique that is based on molecular simulations, much more than data science. And then I want to talk about sort of using data science tools to expand that. And this is what I sometimes call the modern molecular materials screening method. It's really widely used now across material science by modelers. And it really combines kind of three parts. One is just quantum mechanical simulations, which are done now in a high throughput way, so you can run thousands of them with relatively little human effort. The other is large databases of pre-computed information, which often have hundreds of thousands or even millions of data points, which you can use for comparison. And then the third pillar is some physical or data-centric type model. For example, if you want to think about conductivity, maybe you need to understand defect chemistry, and you might get defect information from quantum mechanics, but you need to use the physics of defect chemistry to help you think about ionic transport. So we're going to put those pieces together here, and I think there's a lot of science problems and materials design problems you can tackle with these three pillars, and you'll see papers like this quite widely. So for our particular screening, there are three properties I want to focus on, which I think are the most important. They're not the only important ones, but they're kind of the most important for these solid oxide fuel cell cathodes. The first is they have to be active with respect to oxygen exchange. You have to be able to move oxygen into them and move oxygen through them quickly. The second is that they need to be thermodynamically stable. They're going to work for 5-10 years at 600 degrees Celsius. If they're thermodynamically unstable, they're almost certainly going to come apart. So they need to have good stability, and they need to conduct electrons because they are an electrode. So electrons have to move in and out. So let's talk about how we might screen these. And in fact, this first one was really the stumbling block, I think, for most people working on this, which is that we cannot predict the surface exchange coefficient from molecular simulation. So that's what this K star is. I should say that. This is what's called the surface exchange coefficient. It measures how quickly oxygen can enter and leave the material. And it's a great measure of the activity of the material, how well it's going to grab oxygen and pull it in and make it usable for the fuel cell. If you have a high K star, usually you have very good transport of oxygen, you have good exchange of oxygen. If you have a low one, it just kind of sits there and doesn't work as a catalyst in the cathode. So we want a high K star, but it's a complicated catalytic process bringing oxygen into this material. So we can't really predict it in any rapid way from molecular level simulations. So here we are going to already start thinking in a kind of data-centric and correlative way. What we're actually going to do is calculate a property we can calculate from quantum mechanics. That's going to be the x-axis. And then I'm just going to plot the surface exchange coefficient of a bunch of materials as a function of that property. And what we're hoping for is that there's a strong correlation, and then we can use that correlation to do design going forward. This is a technique that's sometimes called the descriptor method. It's been widely used in catalysis. You take as the x-axis something you do understand and can get quickly. You take as the y-axis some catalytic behavior that is complex and you don't understand that well. And then you try and correlate them with each other. And I won't go through the physics of why this correlation works, but this is called the oxygen p-band center. It basically relates to the energetics of oxygen. So it makes some sense that the energetics of oxygen relates to the surface exchange coefficient of the same atom oxygen. And you can dig into that in more detail, but the correlation looks reasonably good. So we can use this now to take any material, calculate the p-band center, and essentially read off from this line what surface exchange coefficient we think we're going to have. So that's our first pillar that we're going to build on. The second is we're going to calculate thermodynamic stability. Here we use these large existing databases and tools that are in them. You can now do a calculation of essentially any oxide and use pre-built tools from the materials project effort to automatically check, is it thermodynamically stable with respect to other known oxides that are have been found already in nature. So we'll do that, and we'll just throw out things that aren't stable. And then to check if it's an electrical conductor, we're going to use a pretty simple technique. We're just going to look for very small band gaps. If it has a big band gap, it's almost certainly an insulator. Small band gaps don't really prove you're a good electrical conductor, but they at least suggest you have a good chance. So it puts it in the category of maybe worth looking at. So those are the three things we're going to calculate. And then we're going to basically make a kind of inverted funnel to do this type of screening. We're going to run in high throughput quantum mechanical calculations, thousands of perovskites. We're going to do about 2,000 promising systems using some automated tools, basically MAST and the vast electronic structure code. And then we're going to use this correlation I mentioned to predict. We're going to calculate p-band centers with the quantum mechanics. We're going to use the correlations to predict the surface exchange coefficient, and we're going to throw out everything that's not better than present commercial materials. So we're going to keep things that are better than present commercial materials. Then we're going to look for what's thermodynamically stable. So we'll calculate the energy with quantum mechanics. And then we'll take whatever's thermodynamically stable and we'll keep that on our list. And then we'll calculate the band gap with quantum mechanics. And we'll keep whatever has a nice small band gap on our list. And that will be our set of promising materials. That's basically the spirit of this. This screening was published a few years ago in a paper in Advanced Energy Materials, if you want to see the details. And so we go through that, and we did that. And here's what we ended up with. These green triangles are new materials that we found after our screening that we predict to be stable, have small band gaps, so decent conductors, and have high surface exchange, in other words, highly active as cathodes. There's about 20, 25 pretty exciting looking materials here. So then we start the next stage, which is to say, well, should we go off and make some of these, try and use them for something? And here I think it's really interesting to think about and important to think about what are these kinds of computational predictions? How do we think about them when we're doing real materials development? And here's the way I've kind of decided to think about it. I like to think about it as a sort of robot colleague you have in your lab. The humans in your lab have a lot of common sense, they have a lot of understanding, and they have some facts at their disposal, but they're often missing a lot of facts, right? They forget things, there are papers they haven't read, they get distracted. Your computational colleague has no common sense or understanding, so they will make really dumb, goofy, irrational suggestions. On the other hand, whatever facts you've made available to them, they have them. They don't forget them, they don't lose track of them. It's often many more than you might have as a human being, because it's easy to store things in your computational robot colleagues. So the way that I think to use these is to really look at what they suggest, what predictions come out of your robot colleagues, but then to process them through your common sense and your intuitions. Otherwise, you can go off on a lot of wild goose chases of really irrational compounds. So that's what we did here. We looked at all these predictions and we settled on one that seemed to us the right balance of new and interesting, but not crazy and bizarre. And this was a barium, iron, cobalt, zirconium perovskite oxide. It comes from a family of, that I sort of described down here, of barium, iron, cobalt, niobium, tin, yttrium, zirconium perovskites, which have been explored and have been shown to have good surface exchange. But what the computer suggested is that we could get to very high zirconium content, and that would dramatically enhance the stability, but not reduce the surface exchange coefficient, which would mean it would still be a very good active electrode. Most people don't explore very high zirconium content. There was essentially no work on high zirconium content alloys like this, because zirconium is not catalytically active. It is not a transition metal. You don't really expect it to make a good material. So you think if you're 3/4 of your B site in your perovskite is zirconium, most intuitions tell you that's not going to work. In fact, that intuition is so strong, and people had looked so rarely at these high inactive element dope materials that we were able to actually patent this material and these classes of materials. And we thought this was a new place to look, but not so new that it was a crazy place to spend some of your energies. That's how we balanced what our robot colleague told us. So we went out and we made this material, and we actually measured its area-specific resistance. This is actually how well it would work in a fuel cell. So we call it BFCZO. Here it is with a gadolinium doped ceria electrolyte. That's this green dots versus inverse temperature. The orange area is kind of where you want to be. That's your sweet spot to be commercially viable. If your area-specific resistance is not below 0.1, no one's going to even consider it. And you can see at 800 Celsius, even 750 Celsius, we do make it into that range. However, that puts us essentially on par with existing commercial materials, which isn't going to cause anyone to look seriously at modifying their fuel cells because it's not dramatically better. But we realized that a lot of our resistance was coming not from our oxygen exchange, which we had well optimized, but from electrical resistance. You can remember our screening for electrical resistance was not very clever. It was based just on band gap. It was pretty simplified. So we actually ended up with a pretty highly resistive material. A way you can solve that problem is you can make a composite of the electrode out of your high-performing oxygen conducting exchanging material and another good material, maybe not quite as high-performing, but has good electrical conductivity. And the composite often has good electrical conductivity. So we did that. We took LSCF, which is the present state-of-the-art, best-performing commercial electrode, and we made a composite with our material. And you can see that the area-specific resistance dropped by almost a full unit on the log scale. So that's almost a factor of 10 improvement in your area-specific resistance. That means your efficiency or your inefficiency went way down. And what that lets you do is start going to lower and lower temperatures and still staying within the range that you would want to stay in. So if you want to stay below 0.1 in your area-specific resistance, you can now get down to 650 Celsius. So that gets you into the range of intermediate temperature fuel cells, which are around 600 Celsius. This was one set of experiments, so it's really not fully optimized. I think we could be confident that with a little bit of optimization, we could probably get this to perform at a commercially viable level at 600 degrees Celsius, which makes it an exciting material to consider for intermediate temperature fuel cells, which is where people are trying to take these. Now, I don't want to overstate what that means. It just means it's maybe worth considering. There are many factors in terms of long-term durability, in terms of thermal expansion, cycling, costs of manufacturing, et cetera, that would all have to be considered before you would know whether this is really promising for potential commercial application, but at least it's interesting. So let me wrap up there with our story using what I would call sort of traditional descriptor-based DFT, quantum mechanical-based design of the material. We combined this sort of data-centric p-band correlation with high-throughput DFT, and we did find a new cathode material. It also taught us something, that these inactive elements at very high quantities were okay. Actually, you can keep FACS oxygen transport. You do have to worry about electrical conductivity, but even that may be manageable by making composite systems. And we actually found a concrete example that emerged as really an interesting new type of fast oxygen conducting material. Okay, so now I want to sort of put that aside and say, can we bring in emerging, exciting new tools in data science and machine learning to do more or do more efficiently the type of design I just described? So there's a lot one can do in this space, but I want to describe two things that we've been working on to give you a feel of how new or even some old data science techniques can really help this type of materials design. So the first is I want to show how we might use machine learning to more quickly predict the properties that we used quantum mechanics to get at in the study I just showed. And then I want to show how we might get more data for building data-centric correlations from natural language processing methods. So let me start with the idea of predicting properties we care about. So you may remember in the study I just showed, we looked at log of the surface exchange coefficient. That was really the key property that we were trying to optimize. We obtained it by correlating with a quantum mechanical measurement. a quantum mechanical calculation, sorry, I should say, where we calculated the p-band center. That was much easier than trying to actually calculate the surface exchange coefficient or measure it, but it still takes a half a day or a day to do the calculation. So when we ran 2,000 materials and we fixed bugs and stuff like that, that took us a year to do those calculations. And we certainly are not going to do 2 million materials. That would take us a decade or more. We'd need a ton of computing time. So although we can do a pretty impressive search of the space, thousands of materials, that's orders of magnitude over what you'd want to do experimentally with this type of computational approach, we still can't screen a material a second. We screen a material a day. So another idea is, what if you could get that surface exchange coefficient more directly from some kind of machine learning model on a very simple property? And here we're going to explore whether you could get it from what are called elemental features. Here's the idea. What we really want is log of the surface exchange coefficient as a function of the composition. I just want to be able to feed it a composition and have it say, this is your surface exchange coefficient. And we're going to assume they're all perovskites, so there's no differences in structure, really. They're all the same structure. So all I'm really changing is the A and the B cations, and I just want to feed it an A and B cation, and I want to get out a surface exchange coefficient. That is just a correlation. That's the type of thing that machine learning is good at learning. So we could maybe fit this function out with machine learning. If you're going to do that, you need to featureize your compound. You can't tell it, learn the relationship of titanium and carbon. It doesn't really know what titanium and carbon are, right? I know those are elements, but machine learning models typically work on a vector of numbers. So I want a vector of numbers. So a way that people often do this are called elemental property featureizations, where what I'm going to do is I'm going to take the properties of the element A and the properties of the element B, and I'm going to kind of merge them together into a list of numbers, and I'm going to make that the vector that represents this compound. So for example, I might take a compound AXBY, and I might create a vector whose first element is the melting temperature of A plus the melting temperature of B. That's the properties of the elements A and B, weighted by the composition of X and the composition Y. So it brings in the information about composition X and Y, and it brings in information about the melting temperatures. That's information about the elements. So that number should tell me something about the alloy. And I can do that also for the radii of the alloys, of the pure elements. I could weight those and create a number. I could do it for their ionization energies. I can do it for their densities, and so on. So I can take a list of about 100 elemental properties, and I can weight them in many different ways. I can take compositional averages, I can take maximum, I can take minimum in the alloy, I can take differences, and you can create easily a vector of features that depend on the elemental properties that's 1,000 elements long. And that vector can then be fed into many kinds of machine learning models. In fact, I was just talking with Taylor at the beginning about a new model that he's developed that seems to give really extraordinary performance based on these types of elemental features. So they can be very powerful. So we wanted to see if we could use these to predict surface exchange coefficients. So here's an example of how that worked. So on the left, I have what's called a parity plot. I'm predicting values of the surface exchange coefficient on the y-axis, and I am taking true values on the x-axis, and I'm taking what's called test data. So this is data I've pulled out of my data set. I'm not going to use it for any kind of learning. I'm just going to make predictions based on it after I've done any fitting I'm going to do. And on the left, I used our p-band center technique. I said, the surface exchange coefficient is a linear function of the calculated, quantum mechanically calculated p-band center, and I fit the coefficients A and B, and then I predicted this new data set, this test data, and you can see the correlation I get. It's decent. I get a mean absolute error about 0.7 log units, but the time to do one prediction for a new data point in this correlation is about 10,000 seconds, right? It's a few hours, because I have to do a full quantum mechanical calculation. Now let's go over here to the right. This, I did the model with what's called a random forest method. I took the elemental properties of the compounds I was dealing with. I built that vector like I just described. I fit a machine learning model called a random forest model. It's a decision tree type model, typically quite accurate and quick to fit. Took about once we built those elemental properties, took about 30 seconds probably to fit this model. And I predicted the exact same data I'm predicting over here. And the predictions, actually, I should be careful. It's not exactly the same data. It's a different size. It's a different set of test data, but the same size data, basically the same approach. And I get a smaller mean absolute error. Oh, no, I'm sorry. I think it is exactly the same data. I think we use the same data test data set. So it's literally the same predictions. I get a smaller error now, half a log unit, but I can make a prediction now in a fraction of a second because elemental properties are instantly available for everyone. So you can see, as long as I have enough training data for a new set of predictions, I can cut the time to make a prediction by 5 orders of magnitude and actually gain accuracy by using a machine learning method instead of a more traditional quantum mechanical descriptor method. You have to have a lot of training data to make this work, but it looks extremely promising for being able to now screen millions of materials rather than just a few thousand materials. You can do the same thing with the area-specific resistance. Remember, that's actually what we measure in the fuel cell to really decide if the cathode is working. Here's our correlation of area-specific resistance with p-band fit and then assessed with test data on the left side. It actually doesn't work very well. We really don't find very good correlation. We used to find better correlation, but as we've added more and more data, we're not finding very strong correlation. If you use this elemental feature approach, we actually find not amazing correlation because ASR is a pretty messy quantity, but pretty good, and a mean absolute error of 0.4 log units. That's actually enough to make useful and meaningful screening. And again, our prediction time is almost instantaneous. So we're excited now to take these fitted machine learning models and go out and screen not 100 materials or 1,000 materials, but hundreds of thousands or millions of broad scope possible materials. We have not done that all yet, so I don't have the punchline yet of whether it really tells us about new materials, but that's work that is underway. Now, if that part seems exciting, right? We're excited to use these machine learning models instead of having to do quantum mechanics to get our data. To use those models, we have to do a fit. And to do a fit, you have to have data to start with. So, for example, you'll see a lot of points on this plot. These are hundreds and hundreds of area-specific resistances that we went out and extracted from papers. Ryan Jacobs did this over years. Probably took him 2 or 3 years because it's really boring, right? This plot is just a small fraction. We have hundreds of surface exchange coefficients that we used in our databases. So to get those hundreds of data points, we went through thousands of papers over years. And every week or two, Ryan would look at another 10, pull out another data point. And slowly over over years, we collected a few hundred examples that we can now use to fit these machine learning models. That kind of work is tedious, it is boring, it's error prone, you tend to miss a lot, and it's just hard to convince people to do it, so it's hard to develop those kinds of databases. So one of the things we're excited about is, can we use natural language processing to automate that process? And I just want to talk about some very preliminary work, but stuff I'm excited about to explore that. So first, what is natural language processing? So natural language processing is just an area of machine learning and data science that teaches basically artificial intelligence tools to work with natural human language. For example, the text in scientific papers. A kind of state-of-the-art example that we're using right now is called GPT-3. It stands for the Generative Pre-trained Transformer version 3. Some of you may have run into this. They just released about a week ago an altered interface called GPT Chat, which lets you chat with it. I recommend checking it out. You can just Google that. It's surreal how incredible the responses are, how close they are to what humans might be able to do. The way these basically work is they are a deep learning neural network using what's called the transformer architecture. I don't have time to go into that, but it's a relatively recent discovery, past 5 to 10 years, this type of architecture. And what this group did is they trained a 175 billion weight model. So it has 175 billion adjustable parameters, and they fit it to basically the internet. They collected about 45 terabytes of text data, and they trained the model actually in a really simple way. They basically just trained it to learn to predict words that they would mask. So they'd take a sentence, they'd leave out a word, and they'd say, given the sentence, can you predict what that word should be? And through that, it developed an ability to really respond to language and understand language effectively in a human-like way. So what you can do with this type of model is you can do what's called, it works in a generative way. You can give it a prompt, that's some text, and it responds with predicted text that should go with that prompt. And you can essentially give it a few examples of input and output, and it will retrain on those examples and give you out meaningful responses. So for example, you can show it a handful of examples of addition problems. And because it has seen millions of addition problems in all of the 45 terabytes of text, it will start responding with the correct response to addition. It has effectively learned to do addition up to 2 digits. So this shows the accuracy of the model for like 2-digit addition. When you have 175 billion parameters, you're getting near 100%. Now it hasn't learned 2-digit multiplication very well because it didn't have that many examples. But it's extraordinary what these can do. They can actually write code if you give it a prompt, because they have seen so many examples of code from sites like GitHub. And there's a whole subsection of this called Codex, where people are building tools that will automatically write code for you. So these are very transformative technologies. They really are creating the ability to create text that is human-like in a way that was just not possible even 5 years ago. They can literally write academic papers that look like something you would publish. They can write fiction stories, they can write nonfiction stories, they can write usable code that works. They can enter coding competitions and score competently. They can translate, they can do an amazing number of things. So what we want to use them to do is to read papers for us and help us pull out data. One thing I'd say about these is they are growing at an incredible rate. They grow at about 10 times in size every year. So already they went from just kind of amazing in 2018, 2019 to vaguely mind-blowing around 2021 to just disturbing by 2022 in terms of the level of what they can do. It's hard to understand, even fathom what they might be like in 5 years. So it's a really good tool to build on because the pace of change of the underlying models is just extraordinary. What are we doing with it? So what we do is we basically take GPT-3, we gather maybe 5,000 or so papers with standard searches for some property we might care about. For example, something like area-specific resistance or something like that. Or this example, sorry, I thought I just updated this example. This is an example from bulk modulus, but I'll show you something for area-specific resistance in a minute. So we take something like bulk modulus, we give it training example sentences, and then we just tell it, pull out all the sentences that are like these, and it will extract from the text all the sentences that are like these. And you can then automate getting the data out, but what we've decided is that's not worth it. That gets very difficult. We just let a human read the sentences, because there's maybe 500 or 1,000 of them, maybe 2,000. It's tedious, but it only takes a few hours. And then you just put the data into a table. So we did this, for example, for bulk modulus. We went through about 4,500 papers in the last 15 years. We extracted about 750 bulk moduli. We can estimate really how well we're doing by reading the papers by hand. We get about 80% of the stuff we find right. We find about 60% of the stuff that's there. So it's definitely not perfect. We don't read tables, for example, but you do get a meaningful and useful database. So we got this huge distribution of bulk moduli. I immediately thought it was wrong because it had a bulk modulus of 1,100 gigapascals. I was like, there's no material that has 1,100 gigapascal bulk modulus. So I went to the database, found the reference, and I was wrong. There are materials that have been calculated, this is a DFT result, to have enormously high bulk moduli. I also was sure that there were no materials with 30 megapascal bulk moduli that were solid phases. I was wrong about that too. Halide perovskites, which are new solar cell materials, actually have really low bulk moduli. So although it is not comprehensive and it's not perfectly accurate, it took me 10 minutes to start learning things from this database. It knew way more than I knew. And I've actually written papers on bulk moduli and calculations. So I had some expertise in the field, and it still knew way more than I knew. So it really can be useful. Here's an example of us doing this for area-specific resistance. Remember, that's one of the quantities we'd like to be able to fit to machine learning models. It took us about 12 hours to extract about 1,000 values, trivial amount of computing time out of about 4,000 papers. Now, you always have to ask, is this data any good? So I took the lowest 10 materials I could find at 600 degrees Celsius, we extracted it by temperature, and I just list them here. 3 of them turned out to be electrolytes or materials for protonic fuel cells, so I wasn't actually interested in those. But the rest are all real state-of-the-art solid oxide fuel cell cathode materials. And if I was a graduate student and I wanted to get a list of what is absolutely the best materials, this is exactly the right list to have. Nanostructured lanthanum, strontium, cobaltate, I didn't realize it, but that should have been on the list. That's a great material. Barium, strontium, cobalt, iron, that's the best performing material, essentially, that's been discovered. I happen to know that already, and it pulled it right out. So again, it's not a comprehensive database, but it is a super useful database. It gives you meaningful, useful data, and it gives it to you at orders of magnitude the speed it would take if you just read papers, did keyword searches, and tried to pull out the data by. Okay, let me just wrap up. I'm going to skip the last 2, which are kind of some infrastructure ideas, and just summarize and say a little bit what I think this shows. So I showed an example of using high throughput DFT and descriptors and a method to find new materials. That's a really, I think, a standard workflow now for finding new materials. We used it to find new fast oxygen materials. I think it's very powerful, can be adapted in many domains. And then we started thinking about data science tools, and I hope I showed you at least that those really have the potential to give us another few orders of magnitude of speed up in terms of our ability to search through materials. And I think by combining natural language processing to get lots of data and then machine learning models to predict that data, you get the ability to get access to data on a scale that maybe we haven't been able to before. And then, as I said, there's a few infrastructure things I think we need to solve to make these kinds of tools, educate ourselves about them, make them available to everybody. Happy to talk about those more if people want. But I'll wrap up there for now. Thank you very much for your attention.
Awesome. Thank you so much. Panelists' prerogative to ask a question. Bloom Energy, I remember when I was working on fuel cell stuff, like they were around and they're still around. They're growing and
they're still around. They are had raised something, I think, over $1 billion in venture capital.
wow.
So a lot of people believed in them and still do. I believe they have IPO'd and are a publicly traded company, I think, now. I may be wrong about that. I think the jury is out whether it is truly cheaper in the long term without subsidies to run their fuel cell technology on natural gas than it is to be connected, say, to the grid to get your electricity.
Okay.
That's a very subtle number to determine, right? Because it depends what kind of subsidies are available, how often you have to replace components, but they're close enough that people try it, right? And I think it will depend over time, and a lot of that will depend on scale of production, right? How much they can get costs down, things like that.
Yeah.
But it's in the game of being fully competitive with buying your electricity from a natural gas plant and sending it through wires to your company. As you know,
and they use LSMO.
I believe they still use LSM. Yeah, that's my understanding. I'm not sure they're telling people, but that is my understanding of what
okay.
technology is. So I could definitely be wrong about that.
All right, so there are some questions here. So from Sterling Baird, have you considered running the surface exchange coefficient simulations in an adaptive design fashion, either to optimize the value of the surface exchange coefficient or to create a data set designed to minimize model error?
Yeah, that is a great idea. Yeah, well, now I'm considering it. So we didn't really try that, mostly for fear of not understanding well enough sort of how it would go. I felt like if I just blanketed the space of stuff I understood and then fit a model, I sort of had better control. But I think what you're suggesting is, well, shouldn't you take your model, predict your surface exchange, and then do a sort of search in the space to find the next best material? And there's a balance usually of whether you try and make your model better or whether you try and find a better material, and you can trade off those and then iteratively choose the next DFT calculation to run, not at random, but in this really smart way. And that will converge you to both a better model and a better surface to change coefficient. And I think that would be a really interesting thing to do. We have not done that. And there'd probably be some thinking about exactly what's the space that you're going to search through in that kind of active learning exercise. But yes, I think definitely, well, no, there's a little bit of a challenge with that is you would, yeah, so you have to run a DFT every time you go to the next point. So I have to think about it a little more, but no, we have not done it. So I have no really wise things to say about it. Yes, I think it's a really interesting thing to do. It kind of wasn't where we started, but I think it's definitely a nice way to approach these kinds of problems.
And then another question is, what advantages does the GPT-3 sentence similarity approach have relative to rule-based schema?
Yeah, I'd say the advantage is it's borderline mindless. Meaning I can literally write down, say I want to search for bulk moduli, I can just write down sentences I think sound like the kind of things you might have in scientific papers. Like it takes seconds to just be like, the bulk modulus is 73 gigapascal. Silicon has a low bulk modulus. Like I can just make stuff up and those will work as training sentences. And then I can make stuff up that is like, James Joyce is a really confusing author. And I can send it that. And it will be like, okay, those are bad sentences. And I just tell it, these are good, these are bad, and it learns. If you want rule-based schema, you have to go through this really painful exercise of being like, how many ways is there to write the word gigapascal? And then like write the regular expression scheme to like check. And then like, how many ways do people discuss bulk modulus? And how many ways it becomes this very tedious, like library development of all the rules you need to think about. GPT-3 has somehow learned how to talk to me as a human being because it is a natural language machine. And I can just give it these very natural prompts. And those are very easy to generate and very non-tedious. Like you can almost automate it. And so it really removes a stage of these types of searches that is otherwise time-consuming and painful.
So how do you see, I mean, there's been kind of, I've seen a lot of stuff like on Twitter this week about ChatGPT and doesn't seem to understand probability very well or certain kinds of math problems, and those things are gonna get better. But do you see it as, well, the human scientist can do those things and make it do the really tedious like paper reading and pull out the data that you want?
Yeah, so I think there's exciting things to do in both paths, right? So there's one path where you say, I want to get these language processing tools and ways to use them to the point where I can automatically pull out the bulk modulus from every paper ever written with like 95% fidelity. And to do that, I want to be able to read old papers. I want to be able to read tables. I want to be able to automate finding everything. And that's super hard, but amazingly powerful, right? If you get there. And once you've done it forever, right? So I think it's a great thing to work on.
Okay.
But it's hard, right? And you tend to create a lot of databases that aren't very useful along the way, and you spend 6 months doing it. Before we get there, there's a sort of human in the loop approach, which is what we've taken, where you throw in a bunch of training sentences, prompts. You spend an hour writing them down, and that evening you have a database. Right? You have to spend 5 hours reading boring sentences and typing the bulk moduli I found, or saying no, I'm not interested in that sentence. So that's tedious, but it's like 5 hours type tedious. And it's a one-day exercise to build yourself a reasonable database. So I think it's just two different ways of tackling things. That's how I would think about it.
I really like the way that you conceptualized the sort of human scientists with their strong common sense and understanding, but maybe not so good at remembering things, and then your robot colleague. That was nice. So there's another question. Will there be an open source example or tutorial of running GPT-3 to create a materials database? So going from literature download to final database.
Yeah. Meaning like, will we share some way to do this? So we will and are writing a paper, and that will be sort of the guide. And then ideally, if we write the paper well, there will be a really trivial to use like Jupyter notebook that you can just play with. Can't guarantee we'll write the paper well yet. Depends how easy it is to get what we've hacked together into that form. Because this human in the loop, so this is what I discovered about human in the loop, right? When you say human in the loop, you can have human in the loop where you don't do anything to help the human, or you can have human in the loop where the human writes all these little scripts for themselves to make things easier.
Mm-hmm.
And Mache, who's been working on this, is a really good script writer. So it only takes him 3 hours, but that's because he's hacked together these little tools that present the sentences to him on a screen, and then he presses yes and no.
Mm-hmm.
And all that stuff is not in a nice package Jupyter notebook. So if you really just use the tool in its raw form, 6 hours becomes 12, becomes 20, gets more tedious. There are some trivial ways to turn it into a short human time, but we don't have them all packaged yet. And I think that's true of any human in the loop example. You always want to be a little careful. An expert human in the loop who's helped himself a few times or herself, they're much faster than a brand new human.
Yeah.
So
yes.
There are tricks that are often hidden. So we've used some tricks to get this down to 3 hours. I hope we will put that all out there in the public domain, easy to use form, but I haven't worked out how that will work.
So how do you see, you had kind of there at the beginning, Materials Genome Initiative, and high throughput screening was a very big part of that. And that approach has really kind of been developed a lot and sort of matured. How do you see things now in terms of where the field is now and sort of where it's going?
That's a big question. Yeah, so I can give my own like super biased parochial answer as best I can, which is that I think, yeah, there was a huge success. I mean, Materials Genome had a lot of aspects, but around this sort of molecular modeling stuff, it really worked to streamline ab initio calculations and a lot of other molecular modeling and get big databases out there and make them accessible. And Materials Project is a poster child for that, where it's really worked well. And I think that has changed what we can do in terms of efficient materials design around that. And I think there's a lot more data in general, just a data-centric way of thinking, many more databases, much more shared, and that has changed what you can get your hands on. I think a big thing that will happen is we'll just machine learnify all of that, right? There's really no reason to have a database. A database to me is just a bad machine learning model, right? Because it's just the actual numbers with zero ability to interpolate. A good machine learning model will just return the database plus some interpolation. It's just database plus. So it seems to me we should have every database feed through a machine learning model with some decent uncertainty quantification that gives you back everything in the database plus some interpolation and a little bit of extrapolation and some guidance on how to use it. And then that should just be all cloud accessible. And I think that will just give us another factor of 10, 20%, 50%, some cases orders of magnitude growth in the data and accessibility that we have already gained. And that doesn't have to be DFT data. You can do that on experimental data and things as well. And that's sort of near term, I think, that will happen in the next 5 years.
So like ICSD, obviously big crystal structure database, for example. So what would a machine learnified version of that look like?
Yeah, so it sort of depends maybe how one's thinking about it, but so an example of that might be yeah, I should be careful. I'm thinking more like of a situation where you have a property database,
Okay.
and then you have crystal structures. And a machine learnified version of that, to answer a slightly different question, would be the ability to get properties for whole new crystal structures that you didn't have in your database.
Okay. Okay.
That would be one version. But I think there's a version of what you described too, which might be a generative model built on the ICSD, where you give it a text prompt. I want a silicon dioxide structure with this density and this nearest neighbor thing, and I would like it, to be this stable. And it uses everything it's learned, and it feeds you a new effective ICSD entry with that property as best it can.
Yep.
And if that already exists in the ICSD, you just grab it, right? And
Yep.
So it doesn't have to generate it. But if it doesn't exist, it would say, well, this packing is plausible, and it would typically have a low energy, and it's perfectly reasonable. And,
Yep.
and literally with what we can now do in the last year or year and a half, you literally could write that out as text. Like you could just speak it into your phone, for goodness sakes, and it would process it, turn it into a call in the data language, and then use the generative model built on crystal structures and properties to say, here's what is a good candidate. And that is not science fiction, right? Like that is totally buildable. I can't guarantee how well it would work, but you can build that with technology we have totally available today that's open source. So I think we'll see it in the next 5 years.
I could keep going here, but I'm not going to. Taylor and Frank, did you have?
This was such an interesting talk. I'm just curious more about like where we've seen the ChatGPT does a great job of inferring context, and it does a great job of, I've heard people describe it as like a BS artist, and I think that's a fair description because it messes up these accuracies. So could you comment on, like, if you wanted to purify this data and go through and clean it, what steps could you take to sort of go through and try and clean the outputs that you're using to build your database? Because I think it's a phenomenally interesting idea. How can we make the data cleaner that comes out of it?
Yeah. Well, and let me separate two things. So GPT-3, when used as a factual producing engine, has some serious issues. It's not really fair to GPT-3, right? That's not what they guarantee. But it's so good sometimes that people want to use it that way, right? So you want to ask it like, who's going to be the next president, or who was president in 1976, or something like that. And oftentimes it will tell you the right answer, but then sometimes it will tell you nonsense, and you can't tell the difference because it sounds great either way. And then people are kind of like, wait, this is super dangerous. And that's true. You don't want to use it that way without being really careful. We're not asking it to do that. We're going to train it on sentences, and we're going to ask it the probability of a sentence it reads in the text. What is the probability this matches the training data? So we're not asking it to tell us things about presidents or use of copper in China or anything like that. And so we're giving it training data and letting it adapt to that. And then it can still be wrong, but it has a much better chance of being right. And we can assess whether it's right. We can check in different examples, and we can add more training data if we don't like what we're getting, just like any traditional machine learning type problem. So we're not really subject to the bullshit problem of GPT-3 in that way. It's just regular inaccuracy of any machine learning model that we face. So though, given that, you still have inaccuracy from what it finds. And it's of, I'd say, two kinds. One is sort of, it just doesn't find it. It has, it gets the wrong sentence, or it just misses a sentence because they're not in the right place in the text. I honestly don't know how to solve that problem. I think that is an area of really smart machine learning, meaning we're doing a pretty primitive thing. We're breaking it out one sentence at a time. We tend to look, and when we're asking GPT-3 to rank that sentence, and we just do that with the whole paper. There are probably smarter things to do, like where you sort of encompass the whole paper, where you work across whole paragraphs with some, long short-term memory type algorithm. There's probably things that are deeper than what we're doing on the machine learning that can work more intelligently with the text when stuff is spread out over the whole paper. And I think you may need to do that to solve problems where, like, the bulk modulus value is given in one section and the material is given in another, and stuff like that. The other is we don't know how to read tables, and we don't know how to read plots. I'm not going to solve that problem because people who really care about that and have a lot more money and skills are probably going to solve that problem. So I think that will solve itself. because computer scientists will work on that problem and are getting better all the time. We didn't even try. Like, we didn't even try and read PDFs. Everything we read was XML, because that's the easiest thing to read. There's a whole nother problem of parsing text from PDFs, parsing text from tables, parsing text from pictures. It's not text, parsing data from pictures. That is a whole computer science problem in itself. We haven't touched that. I'm thinking that's actually reasonably far along and will keep moving along on its own. And we as material scientists can just pull from that. You know, it will probably get solved pretty well. Also, people will stop putting data into figures. So yeah, we'll never read papers maybe from 1950 very well, but most of the data generated in the world will be generated in the next 10 years. And I hope people will not bury their data in figures. Students out there, don't bury your data in figures. Just put it in tables, or at least put it in digital media better. And so we won't have that problem really as much. That's, I don't know, that's kind of an answer. I'm not sure I really got to all your points there, but
Yeah, thank you.
Anyone else? Well, thank you so much, Dane. This is great.
all right, thanks. Thanks for the chance to chat, and I appreciate all the questions.
And see you in person, hopefully, somewhere.
Yeah, looking forward to seeing people as real humans soon at conferences. Thanks, take
See you
care.
all later. Wonderful.
Yep.
See you. Bye.